Welcome, and thank you for standing by. At this time, all participants are in a listen-only mode until the question-and-answer session of today's conference. At that time, you may press star one on your phone to ask a question. I would like to inform all parties that today's conference is being recorded. If you have any objections, you may disconnect at this time. I would now like to turn the conference over to Sarah Fraser. Thank you. You may begin.
Hi, everyone. Welcome, and thanks for joining today's media teleconference. My name is Sarah Fraser. I'm from NASA's Office of Communications. Soon, 3 missions will launch on the same rocket from NASA's Kennedy Space Center in Florida. This launch is targeting September 23rd at 7:32 a.m. Each spacecraft has distinct objectives, but they're all united by a goal to better understand the sun's influence on our lives, part of a field of science called heliophysics. Today, you'll hear from experts about the 2 NASA missions on this launch, as well as more about NASA's work in understanding space weather to enable exploration throughout the solar system. Our speakers today are Nikki Fox, Associate Administrator for the Science Mission Directorate at NASA headquarters, David J. McComas, IMAP Principal Investigator at Princeton University, Laura Waldrop, Carruthers Geocorona Observatory Principal Investigator at the University of Illinois Urbana-Champaign, and Teresa Nieves-Chinchilla, Director of the Moon to Mars Space Weather Analysis Office at NASA's Goddard Space Flight Center in Greenbelt, Maryland. We'll start with brief opening remarks from these experts and then open it up for Q&A. For those of you who are on the phone line, you can join the queue to ask a question by pressing star 1 on your phone. And with that, I will hand it over to Nikki to begin our remarks.
Thank you so much, Sarah. This is Nikki, Associate Administrator for NASA's Science Mission Directorate. I'm really excited to be here today to tell you about these incredible missions because, of course, as the United States prepares to send humans back to the moon and onward to Mars, NASA Science is honored to be providing the ultimate interplanetary survival guide to support humanity's epic journey along the way. And only NASA Science can send robotic explorers first to where humans cannot yet reach. Our scientific discoveries and technical innovations directly feed into our Know Before You Go rover roadmap to ensure a prepared, safe, and sustained human presence on other worlds. We learned from the Apollo era that beyond Earth's protective magnetic field are lethal solar radiation storms comprised of sudden bursts of high-energy particles from the sun traveling at nearly the speed of light. These storms can have devastating short and long-term consequences for astronauts, spacecraft, and, of course, the technology on board. They also pose risks within the Earth's atmosphere for air travelers, orbiting satellites, power grids, radio communications, and a lot more. Understanding their source, understanding warning signs, and identifying ways to protect against them are high on our list. They're high on our list for the benefit to humanity, and of course they are high on our list for protecting our human explorers and as they go back to the moon early in 2026. Now, NASA is leading the United States to be a space weather-ready nation. This month, NASA, alongside 27 national and international partners, will launch the Interstellar Mapping and Acceleration Probe, better known as IMAP. An IMAP is a mission of firsts. It will be the first spacecraft dedicated to mapping the heliosphere's outer boundary, a key piece in the heliophysics puzzle about the sun's influence on our solar system. To do this, IMAP will spin every 15 seconds to measure the invisible using a very comprehensive suite of revolutionary 10 instruments. It will also be the first mission to use the unobstructed vantage point of the Earth-Sun Lagrange 1, or the L1 point, in the sun's orbit to observe the solar activity, including, of course, space weather. From its strategic position 1 million miles away from Earth, IMAP will provide warnings beginning with Artemis 2 and Artemis 3 of incoming harmful radiation storms faster than any other spacecraft has done before. It will provide roughly 30 minutes notice for astronauts before the input from the sun reaches them. It will use the IMAP Active Link for Real-Time, or iAlert system, which you're going to hear a lot more about from our panelists. Riding alongside IMAP, we are really excited to have the Carruthers mission, which complements IMAP's data and will expand upon the pioneer work of George Carruthers. He had an ultraviolet camera that flew on Apollo 16 and captured the first view of the outermost part of Earth's atmosphere. We call it the Geocorona. And in fact, that camera still resides on the moon today. And it was the first time that we were able to image that sort of outer boundary where the Earth's atmosphere stops and space starts. You will hear more about the Carruthers instrument that is riding alongside IMAP and also the NOAA Space Weather Follow-On L1 mission. And, I will definitely underscore the importance of Carruthers in the understanding of the near-Earth space weather around this little-known atmospheric region. The reason it's little known is because we've had so few opportunities to image it, George Carruthers' instrument being the best image that we have to date. With Carruthers, we're able to sort of stare and take continuous measurements so we can actually see how that atmosphere is changing and how it is driven by what is coming from the sun, and how our technology, including communication signals in the upper atmosphere and power lines on the ground, are actually impacted by changes in this atmospheric region. As NASA sends astronauts beyond Earth's magnetic protection to the moon, to Mars, and hopefully beyond, IMAP and Carruthers data will help mission planners predict and mitigate the effects of space weather for the benefits of all. So we really, really appreciate, as always, the incredible support that we get from our mission partners, from SpaceX, from our friends at Kennedy Space Center, and most importantly, from the IMAP and Carruthers teams. And so with that, I'm happy to kick it over to you, Dave.
Great. Thanks so much, Nikki. Hi, everybody. I'm Dave McComas. I'm the principal investigator for the IMAP mission. So IMAP will explore our solar neighborhood and decode the messages in energized particles, both coming out from the sun and coming in from beyond our solar system. IMAP flies 10 instruments built by many organizations across the country and even a few around the world to study the solar wind, interstellar dust, and other particles in space, while continually monitoring solar weather to protect space explorers and critical satellite infrastructure. IMAP will study the edge of our heliosphere. The heliosphere is the dynamic, energetic magnetic bubble around our sun that the sun forms by blowing out 1,000,000-mile-an-hour solar wind all directions in space all the time. We study this edge of the heliosphere using energetic neutral atoms, or ENAs. These energetic neutral atoms act as cosmic messengers. They're unaffected by magnetic fields, and so they can propagate all the way in from the boundaries to Earth's orbit and be measured by IMAP. By tracking them, we create a big picture map of the heliosphere, which helps scientists figure out what shapes the boundaries, like the sun's movement through our part of the galaxy, the external pressure of the magnetic field from the galaxy beyond the heliosphere, and changes from the inside by our solar wind. So IMAP's contributions to space weather are key to protecting satellite infrastructure and human and robotic space missions to the moon, to Mars, and even beyond. IMAP will provide near real-time observations of the solar wind and energetic particles, as well as magnetic fields, from the strategic point that Nikki talked about, the Sun-Earth Lagrange point, about 1,000,000 miles upstream of the Earth. That provides about a half-an-hour warning for solar wind arriving at the Earth a little bit later than it arrives at L1, and that's helping with our to save our astronauts and spacecraft from harmful radiation coming their way. So, Nikki already mentioned iAlert, the IMAP active link for real time. It's a system that uses 5 of our instruments' data sets to continuously send information back to Earth and provide enhanced space weather information. The system broadcasts more frequently and more reliable inputs to space weather models, allowing for much better prediction and warnings of increases in damaging particles from the sun to global users. These measurements will help us better understand the fundamental physics of the heliosphere, our place in the stellar neighborhood, and how the interaction of solar and stellar winds form barriers against harmful cosmic rays, thereby also helping to protect astronauts. So over to you, Laura.
Thanks so much, Dave. So my name's Laura Waldrop, and I am the principal investigator of the Carruthers Geocorona Observatory. The Carruthers mission is the first NASA mission that's dedicated to investigating not just a frontier in science, but a literal frontier of our planet, namely Earth's outermost atmospheric region. Now, this region, which is termed the exosphere, originates above the thermosphere near low Earth orbit and then surrounds Earth as a tenuous cloud that extends at least halfway to the moon, more than 100,000 miles away from the surface of Earth. We actually don't know exactly how big it is. We don't know whether it's spherical or oval, how much it changes over time, or even the density of its constituent hydrogen atoms. Because as Nikki mentioned, most past measurements have been made locally, well within the exosphere itself. And opportunities to deploy sensors to probe its outer edge are so rare. What we do know is that the exosphere plays a critical role in Earth's response to geomagnetic storms. And this is through its interaction primarily with magnetospheric ions. Now, these interactions not only weaken dangerous storm-induced current systems, but they also replenish storm-induced depletions of the very plasma that shields our planet from harmful space weather effects. Now, this exospheric region is also the path by which atomic hydrogen escapes Earth gravity and is lost into space. Now, the hydrogen atoms themselves are produced mainly from the breakdown of atmospheric water vapor at lower altitudes, and the vapor comes from the evaporation of Earth's abundant surface water reservoirs. Though this process is extremely slow at Earth, and I'm talking billions of years, it is certainly nothing to worry about. The knowledge that we gain about how it works here will help us understand the evolution of other planets and moons in our solar system, like ancient Mars, for example, which famously lost its own surface water through this exact process. And it might help us identify potentially habitable exoplanets in solar systems beyond our own. As a heliophysics mission of opportunity, the Carruthers mission takes advantage of the extremely rare opportunity to measure the size, structure, and most importantly, the temporal dynamics of Earth's vast exosphere from the ideal vantage, halo orbit around the Earth-Sun L1 Lagrange point. From there, the Carruthers mission will look back at Earth and take image after image of the ultraviolet glow that exospheric hydrogen atoms emit naturally when the sun shines on them. We're going to be using dual wide and narrow field cameras, which were developed by the University of California at Berkeley. And the combination of our camera's wide field of view and the distant vantage that we're able to reach through this unique rideshare opportunity with IMAP enable us to capture the exosphere's full extent in a single image frame. We're going to use the measurements of the brightness and distribution of this ultraviolet glow that we see in our images to infer the underlying hydrogen density and its variation in response to solar storms. This data fills a very long-standing knowledge gap and will improve our ability to predict geomagnetic storm recovery timescales and ultimately mitigate their harmful effects on the technological systems upon which modern society depends. As Nikki mentioned, our mission wouldn't be possible without Dr. George Carruthers, a three-time University of Illinois alum who invented ultraviolet imaging technology for his pioneering Apollo 16 experiment. He, in fact, coined the term geocorona to refer to that fuzzy, glowing halo that he was the first to see with his camera. And we're so excited to be carrying his distinguished legacy forward with his namesake mission, the Carruthers Geocorona Observatory. And with that, I'll pass it over to Teresa.
Thank you, Lara. I am Teresa Nieves Chinchilla. I'm the director of the Moon to Mars Space Weather Analysis Office that is located here at Goddard in the Heliophysics Science Division. And this office is just one of the endings of many stories happening in this division and developed by many scientists working in understanding of the space weather and the impact in our missions. So in our office, we function as a proving ground, testing out these new capabilities, experimental capabilities coming from the research community. We do it in real time every single day of the year. We are testing these capabilities and monitoring the data from our missions and providing a space weather assessment for NASA robotic missions and those during operational activities for human exploration. We work very close in this task with a Space Radiation Analysis Group, SRAC, that is located at Houston in the Johnson Center, and the console operator we report to them and provide the expert assessment of the space environment. IMAP will be very relevant for us for many reasons, but one of them is because one of the products, the data products, will be as David mentioned before, the iAlert. That is the IMAP active link for real time. This data, it will be the downlink and observe it almost in near real time, and it will provide information about the solar wind, energetic particles, and magnetic field. 3 data sets, kind of data sets that are critical to perform this assessment of the space weather in the near Earth environment. Scientists will be using this data for sure to learn about the space weather, but in our case, it will be very quickly integrated into the ISY and CCMC. That is another capability here in the Geophysics Science Division. That is this ISY is the Integrated Space Weather Analysis System. That is a platform that display all data in space weather in the near real time, a downlink. And then as soon as this data is here, our analysts will be monitoring the data and performing this assessment. And when we observe any variability in the space weather or impact in our mission, we connect through our notification system with our NASA missions and provide this heads up to them. So in terms of the human exploration, why is this important? This data set is coming right in the right time. So Artemis 2 is coming up next year, and then this data will be also available for those doing space weather operational activities to monitor space weather, a possible impact of the some variability on this operational activity. So in our case, also, we work very close, as I said, with SRAC and CCMC in a project that is Integrate Solar Energetic Proton Event Alert Warning System project. And in this project, we will use real-time data to perform validation and transition of many models from research to operation. This is an ongoing project, and real-time data coming from IMAP will be integrated in this project very quickly. And this is very important not just for Artemis 2, but also to deep space exploration of human exploration in the deep space. In terms of robotic missions, we also support, and we are a capability to support robotic missions in the space. Our goal is to support them wherever they are, and sometimes we don't really know how is the space for these explorers, how is the space weather impacting them. So in terms, we send the notifications, but we also work with the NASA robotic operators to understand how the space weather is impacting on their everyday activities. So again, in this case, we test many of the models that we are using in real time to perform this assessment, and we'll test out with this real-time data. In terms of the community and society, we also work with those doing the official space weather forecast and warnings, sending warnings and alerts to the industry and private sector. We work very close, in this case, with NOAA, Space Weather Prediction Center, and we will work with them in support of Artemis 2. And we also work with many agencies across the world, and we are here to serve them and provide our knowledge and experience with these new capabilities in transition to the operational world in the space weather. Thank you very much. Mm-hmm.
Thank you. All right, so we are now ready for questions. So as a reminder for those on the phone, you can press *1 to get into the queue to ask a question. When you're in the queue, I will call on you and the operator will unmute you. So when you're asking a question, please state if it's directed at anyone in particular. Otherwise, we will have people chime in on those. So our first question will be from Alexandra Witze with Nature. Sydney, are you able to unmute Alex's line? Oh, there we go. Should be open now.
Yeah, I'm unmuted. Can you hear me?
Yes.
Okay. Thanks. My question is for Teresa. Could you talk a little bit more about Artemis 2 specifically and how data from these missions could be used, like specifically during that in real time? I mean, is data going to be flowing back quickly enough to feed into what the astronauts, will be experiencing in real time? Can you just walk me through literally the duration of the Artemis 2 mission and how these data from these two spacecraft will feed into that?
So the duration of the Artemis 2 will be 10 days. In our case, we will be operating 10 days. We usually work we are not fully operational. We work just 14, 15 hours per day. But in those days, we will be fully operational, supporting SWIFT NOAA in the monitoring and forecasting activity. And we'll work also very close, as we do every single day of the year, with the SRAC group, which is in charge of the operational activities. In general, we are monitoring radiation, energetic particles, which is the main hazard for human exploration. And in those cases, we have right now running at, like 7, 8 models that provide information about the intensity, the duration of this, and the arrival, obviously, the prediction of the arrival of this radiation to the Earth environment. So in general, we'll perform what we are doing in real time is provide our assessment to SRAC, and SRAC is in charge to talk with mission control and provide the alert and warning. From there, mission control obviously will make the decisions about how the astronauts will be, acting in these scenarios and situations with different protocols. Mm-hmm.
Great. Our next question will be from Jeannie Donahue, who is a freelance journalist.
Yes, ma'am. This is I guess, question to everybody there. We now have the arrival of what is it, 3I Atlas comet, only the third noted interstellar visitor. Everybody, a lot of telescopes obviously are all over the world, or just you guys too looking at it. What are any of these two missions or these missions going up that we're speaking of today going to be able to send us any information on that comet and how it affects our heliosphere and like drawing plasma from the sun as it comes closer to and makes it what they call perihelion. Excuse me. Anyway, that's my question. It's a big time, only third big comet from outer space. We're big time, right? So that's...
Yeah, this is Dave. Maybe I'll start. It's a really interesting question, and we've been asking ourselves that question. Perihelions, during the time when we're still turning on the instruments,
right.
We've talked about whether or not we'd have enough on that we might see some effect in the energetic neutral atoms. Not sure that we will, but I want to point out that while this is the third big object coming through, we also are measuring on IMAP the interstellar dust, and we expect to collect about 100 interstellar dust particles in the first year of the IMAP mission alone. That's more than all the dust particles that humanity's collected so far. So while we may or may not be able to see something about such a large object, we expect to be routinely collecting lots of little tiny objects from interstellar space.
Yeah, and I'm just going to add maybe to that while unfortunately we will still be commissioning these amazing observatories, they will be completely ready for the next time we see one of these amazing objects. And of course, the rest of the NASA science fleet, there's a huge number of our incredible observatories that are doing a sort of coordinated look and then actually a coordinated study of putting together all of the observations that we're able to take with the incredible NASA science fleet. So these are amazing opportunities for us. It's not often. It's only the third time that we've had an interstellar visitor. And, of course, we're really excited to see what what is in that object, and what, of course, it may have meant for the early solar system for us as we were forming here. So thanks so much for a great question.
You're welcome. Will Juno, the Jupiter, any of the outer missions be able to see or give us any information? Do you know? Well, that's off the topic.
Yes.
I'm sorry.
Yes, certainly. We all of the observing instruments that we have that can see it are doing it, but certainly Juno, I believe, Europa Clipper. I think we're coordinating with other agencies as well on those missions. But really, this is such a rare opportunity. We're not going to miss being able to take observations of it, so we can do great studies and great science as always.
Great. Our next question will be from Marcia Smith with Space Policy Online.
Thanks so much for taking my question. I think this is probably to Nikki because it's sort of a broader heliophysics space weather question. I'm trying to connect the dots between these various space weather instruments that are being launched or have been launched recently, like the CCOR-1 on GOES-U and SWIFO's going along with IMAP. And then there are all the existing space weather satellites out there at L1. How are they different from each other, or how are they the same? Can you sort of connect the dots amongst them? And do any of these newer ones replace the older ones? I mean, like the really old ones like SOHO, or are all of them needed in order to get the space weather data that we need?
I think we take advantage of all of the assets that we have. They all play an extremely vital role, and together, they form one sort of big space weather observatory. Certainly, as we launch newer missions, they often have more advanced instrumentation that can take more sensitive measurements, we will be using them to the fullest potential. Obviously, SOHO is a particularly unique instrument, since you mentioned that with the coronagraph on there. SOHO being an older asset and all of the resources on board focused on keeping that coronagraph going. There will be a small compact coronagraph, the C-Core, as you noted, that will be launched on SWIFO. I defer to NOAA to give details on their particular observatory, but I think it's a great opportunity for us to still have SOHO and that coronagraph working. The new C-Core coming on SWIFO, also the one, as you noted, that launched on GOES-U, and really just being able to put all those together to give us a much, much better view of the sun. And it isn't just about the optical measurements. It is about all those in situ measurements that we get on our fleet that together make us enable us to be able to do the really, really critical space weather forecast on behalf of our nation, which, of course, is one of our administration priorities. And so not only are we going to be able to do the space weather forecasting for our astronauts on Artemis 2 and 3, but we are also able to do full predictions with NOAA. We are kind of the science piece of space weather. We do the first-of-a-kind, cutting-edge measurements and push the boundaries of the research and the modeling, and then work with our operational agencies to actually be able to put out and support them as they are putting out the space weather forecast. So every one of our assets playing a really, really key role in that enterprise.
Great, thank you. Just a reminder to reporters on the line, you can press *1 to get into the queue to ask a question. It looks like we don't have anyone in the queue at the moment, so I'm going to ask a question of my own. I'd like to start with Dave and Laura, and then others can chime in too. Can you talk a little bit about how these two missions build on previous work at NASA? So, Dave, let's start with you.
Sure, yeah. So IMAP follows along behind a much smaller mission, a small explorer mission called IBEX, which launched in 2008 and only had 2 instruments on it. And it was the first to make these energetic neutral atom images of the boundaries of our heliosphere. And because the results were so exciting and such new discoveries were made, we discovered a bright ribbon of emissions in the sky that nobody had predicted from any prior models or theory and things like that. And there was so much excitement in the community that then when we started talking about what's the next big mission we ought to be doing in heliophysics, the National Academy of Sciences runs a decadal survey every 10 years to sort of talk about the evolving priorities in heliophysics. We made our case that, that a big mission doing ENAs on a much grander scale made a lot of sense. The National Academies actually put that together with a difference idea that would look at in situ particle acceleration and energetic particles, charged particles coming from the sun, and said both of those need to go to LL1. What if NASA were to put out an announcement of opportunity for a mission that combined those two sets of science goals? And that was the birth of the IMAP project. NASA did put out an AO, and we competed for it and ended up winning that. And so what we ended up with was this fabulous observatory that measures everything from the particles coming out from the sun that are moving on their way out in the solar wind to get to the outer heliosphere. Some fraction of them become neutralized and come right back in, and we observe them as a few years later as ENAs. So we're really observing the entire life cycle of this particle energization and how it interacts at the boundaries of the heliosphere. It's a very natural follow-on from IBEX, but also it's much, much more than that.
Great. Laura, do you want to go ahead?
Sure, yes. So this is Laura Waldrop. So as I mentioned in my earlier remarks, there have been extremely few images of Earth's exosphere or geocorona taken from outside the geocorona itself. The first was, of course, the Apollo 16 images that George Carruthers obtained. But since then, there have been none other, apart from single instances from as essentially secondary, bonus science from missions that had other purposes. The predecessor exospheric missions that we're currently drawing our knowledge from are the time spacecraft had an ultraviolet imager on it, essentially a spectrograph known as GUVI. That one was in low Earth orbit, and then the twins pair of satellites that were in a highly elliptical orbit, but still Earth orbiting, had cameras pixels really, single pixel detectors that could measure this ultraviolet emission that the exospheric hydrogen atoms give off. So both missions, though, were essentially one or a few pixels, and then they both employed mechanical scanning around the exosphere to try to sense its different portions. And therefore, they didn't really have global coverage. In order to build up global coverage, they had to essentially scan for a really long time. So there was a trade-off with being able to understand the temporal variability. They could get, for example, a global picture, which was a seasonal average, or they could get a local snapshot of time variation, but they couldn't do both. And so what the Carruthers Geocorona Observatory does is by getting so far away, we're able to have, a million lines of sight essentially in every image looking at the observatory. So we have a million pixels at any given time, and then we acquire those images every 30 minutes. And so we're able to also then see the temporal variation at the cadence we need to understand its response to geomagnetic storms. But apart from the Apollo 16 camera, there hasn't really been, NASA has not deployed a camera like this since that 1972 mission.
Great, thank you. We do have a couple folks in the queue now, so let's go next to Alex Whitsey from Nature.
Hi, can you hear me this time?
Yes.
Great, thanks so much. I wanted to ask Dave McComas a little bit more kind of on how IMAP builds on IBEX. Like I remember that IBEX ribbon discovery, and that was kind of one of those fundamental crazy things, right, that we didn't know was coming. Do you foresee that IMAP will be able to sort of make big, surprising scientific discoveries, like things we didn't know were existing out there? Or do you think this is more of like a long-term monitoring and understanding the system more? I wonder if you could just talk about, kind of surprise, whether you think we're going to get surprises or whether you see this as kind of more of a monitoring and understanding the system. And maybe the answer is both, but I'm curious what you think.
Can you hear me?
Yes.
Yes, great, thank you. That's a great question, and we were so thrilled when the discovery of the ibex ribbon occurred, and we got the cover of Science magazine and a bunch of articles and all that. The amazing thing about any of these space missions, and this isn't just ibex or IMAP, is, you design your mission around the stuff that you know, and you're sure you're going to make better measurements of that, and you're sure you're going to be able to really push sort of the forefront of the areas that you know enough to ask the right questions. But you also know that if you build the right instruments and fly the right mission, that you're going to make new discoveries, but you don't know what they are. And so, that's sort of the story of IBEX. That's the story of a lot of our space missions. And what's super exciting about us is that we can do both. We know that we're going to be doing a much better job, much higher precision, much better understanding of the interaction of the solar system with the local interstellar medium. We know a lot of things that we're going to be able to do that we just can't answer with the resolution and sensitivity and capabilities of IBEX, for example. But also we know that by having a factor of, say, 30 to 50 better times sensitivity and resolution compared to IBEX, there are going to be new things that we're not able to see that we don't know about yet. And so I look forward to a couple of years of really great discovery science on top of all of the great things that we know we'll be doing anyway.
And maybe I'll just add to Dave, the overwhelming answer to that question, Alex, is yes. We are going to find incredible new discoveries. We have totally different instrumentation. So looking at IBEX, as Dave noted, there were 2 cameras on there, 2 ENA images that were on there. We have a much broader swath of energy. We have much higher resolution. And together with that, we have all of the in situ measurements. So being able to pull together the entire puzzle, what is coming from the sun, what is coming from the interstellar medium, and putting it all together on one observatory. And so I'm excited about the space weather applications. I'm not going to lie, because that is such a real world thing that we do for the benefit of the nation. But the actual discovery science that we will get from IMAP is going to literally rewrite textbooks, and that's why we're so excited about it.
Great, thank you. Our next question will be from Jeannie Donahue, Freelance.
Thank you. My next question here is about the your missions that are measuring the solar wind, interplanetary events, all kinds of storms, things. What's to protect your instruments? The missions themselves being up there, floating around the heliosphere, no doubt getting subject to cosmic rays, if not solar rays, and of all kinds, and of course space junk, clearing space junk. If that gets in the way, that's a big problem. So. If you could address any of that, that would be interesting, I think. Thank you.
Yeah. That's another really interesting question. And, of course, we design our missions to be able to withstand whatever is thrown at them. We do a lot of work. We build on the legacy of missions that have come before, making those measurements, telling us what to expect. And, I'm going to talk about Parker Solar Probe for a minute. We're flying through the atmosphere of a star. We've done it. We're coming up for the 25th flyby in the most intense radiation and heat we've ever had to deal with a mission. We design these missions for the environment that they're going to operate in, and often we get questions like, are you worried about like a big solar event happening that is going to impact your mission? And my answer is always no. I'm worried that we won't get one, because we are designed to actually look at the full range of activity coming from our star, and we want to see the full activity, and we have every confidence in IMAP and Carruthers returning the most incredible data for us, showing us about the full variability of our sun.
Wonderful. Unless any of our other speakers have anything to add for that question, I think that'll be the end. Teresa, go ahead.
I may add something also very interesting. As Nikki mentioned, our missions are very prepared to be exposed to sun radiation when they are in the deep space. But I would say also that some of these spacecraft are also exposed to the response of the magnetosphere or atmosphere of the planet to this space weather activity. So in our case, in the Earth environment, many of the missions satellites are exposed to this response of the magnetosphere to the space weather. And sometimes we don't have all the information that is necessary to protect them. And, in general, nothing happened, just data gaps or maybe lack of communication, but it may be relevant. And this is an area that we are also looking for how to understand better the response of the technology to this space, the magnetosphere effect of the space weather, as well as in the future maybe Mars or any other planet that they have their own atmosphere, and there will be orbiters there that will be exposed to this new nature, new environment that we are now knowing or looking for how to learn more about them. Mm-hmm.
Wonderful. Thank you. So we will wrap it up there. Thank you all so much for your time. So for those listening, a recording of this call will be available shortly by dialing 800-873-5860 with passcode 6598. If you are listening on YouTube, you can also use that same link to listen to the recording, and that's available on nasa.gov/live. For the U.S. media who are on the line, you can still apply to attend this launch in person until Monday, September 8th. So you can find more information about how to apply at nasa.gov/IMAP. This website also has other information and resources about the mission, including some new material that we published at the start of this call. For everyone, we hope that you'll tune in to watch the launch of IMAP, Carruthers, and NOAA's Space Weather Follow-on L1 mission on the morning of September 23rd. You can watch the launch on NASA Plus, nasa.gov/live, and on NASA's social media channels. Thank you.
That concludes today's conference. Thank you for participating. You may disconnect at this time.